we've been introduced to a single partial derivative, but now we want to think about the idea of multiple derivatives in the partial space. And it's a little more complicated than it was in the introductory calculus, where we would take f prime, f double prime, f triple prime. So if we want to take multiple derivatives, what we do is we apply the operators in a particular sequence. So for instance, to find the second partial with respect to x, we find the first partial with respect to x, and then we find its derivative. So, and we write this, we could write this also as f, instead of fx, it's fxx. And that's pretty much like f double prime in, the standard introductory calculus. But if we start moving over here into something where we have a partial with one direction and we have a partial with another direction, then we have to be a little more careful. So if I take the second partial with respect to, or if I take the partial of f with respect to y and respect to x, this notation tells me that I've taken the first partial with respect to y, and then I take its partial with respect to x afterwards. So I take the derivative in y, and then whatever I get, then I take the derivative in x. Notice that this is written slightly differently. This writes dx dy to kind of break this out, but this puts the y first. This notation is saying that y is what I did first, x is what I did second, and so on and so forth. So this notation lists them in order of operator. This one lists it more in sort of that chained logical order. Derivative of x, derivative, it's like think like parentheses. Derivative with respect to x of the derivative of respect to y of f. That idea. So if we look over here, this should be dy dx. Then this order is, we take the partial with respect to x first, then we take the partial with respect to y, and we write that as fxy. So again, the partial with respect to x first, and then the partial with respect to y. So we have, these things are different. The order does matter. And finally, if we want to take some sort of third partial with respect to all these, now there is the case, by the way, where it could be dx, dy, dy, or something to that effect. But in the case where I have three operators, the same idea. This is broken up this way, but this is reversed to say we take the partial with respect to z first, y second, x third. So really it's just a matter of convention, but it's important to point out that that's how we do it. And we're going to do some examples to kind of show how to do all this. But the one thing I want to point out is, which is super convenient, if it turns out that these second partials are continuous, then you can always swap. You can do them in whatever you want. And so if you kind of look at what you're dealing with, then it should be fairly obvious. But sometimes you have to kind of do both sides to determine they're continuous, and at that point, you're not really that helpful to swap them. But this can be very important if you're dealing with something with like three variables. It allows you to mix and match as long as you have the same number. So I'm going to write something else like, as long as everything was continuous, fxzz is equal to fzxz or zzx. So you basically could do whichever one's convenient. So a nice thing might be somehow if there was not any x's in the first place, you could go ahead and take this derivative first. Everything would be zero, so the rest of these are zero, as opposed to having to painstakingly do something, let's say it's nasty, it has z's everywhere. Well, then you were doing a whole lot of work just to get zero. So try to save yourself some time.